Okay, for this section, more on functions and their graphs. Here's the idea for chapter 1 and also for chapter 2. The main goal for both of these chapters is to be able to identify functions, and then secondly, to be able to graph them. So our whole goal for chapters 1 and 2 will be to examine all the aspects of functions, and then how do we graph them? That's going to be our goal. What I'm going to show you is in graphing that you'll be able to graph all of these functions. We're going to do them by hand. I want you to be able to see that so that you actually understand the mechanics in terms of graphing. Not so much with a graphing calculator or a computer, and maybe one day or so I'll pull something up and we can make a comparison between being able to take a function, graph it by hand, and then compare that with maybe a graphing utility or a computer-aided device. So here for this section, more on functions and their graphs. Want to be able to identify the intervals of which function increase, decrease, or if function's constant, and what does that mean? And then to be able to talk about if a function has a maximum, if it has a minimum. It may have more than one maximum. So we can talk about relative maximums. That is, maximums within a certain location, within maybe a small interval. So we can talk about maybe this maximum here, maybe there's another maximum. So maybe like it has like a camel back. And so we have several, high slopes and that kind of thing. It may have more than one minimum, so we can talk about relative minimums. That is particular minimums when we have, say for example, more than one. And then maybe somewhere we'll raise the question, is there a difference between a relative, we call these maximums or minimums, we call them extremas. Is there a difference between a relative extrema with respect to an absolute extrema? That is it possible that a function has a relative minimum, but then the question may be, does it have an absolute minimum? Or it may have an absolute min or max, but it may not have a relative. And so what does all that mean? Now those questions are important, especially for calculus, because in calculus we'll be able to use the so-called derivative or the derivative test to be able to determine whether or not a function has a relative minimum or a relative maximum. So I think this is a pretty good introduction to that in calculus, because that's most important. It becomes basically 50% of why we study calculus. And then from there we look at various aspects of a graph. Is there symmetry? Is there a mirror image with respect to the x-axis? Is there a symmetry with respect to the y-axis? Or is there symmetry with respect to the origin? And what does all that mean? And then we lastly talk about, well, before the last topic, we talk about odd and even functions, which also has something to do with the so-called symmetry of a graph. And then lastly, we end with this difference quotient. And I want to talk about that when we get to it, because that has also rich properties for calculus. So first, let's talk about increasing and decreasing functions. A function is increasing on some open interval. So we say that we have some open interval. Some open interval I hadn't been down in a long time. Most of my classes are online. If a function at a value x of 1 is less whenever x of 1 is less than x of 2. So here's just the idea. If I have an x of 1 on the graph and then an x of 2, so x of 1 is less than x of 2, does that also imply that the corresponding function values are also in that regard? X of 1 less than x of 2? Does that imply that f of x of 1 is less than f of x of 2? Well, if that's the case, then the function is going up. Now, if we get the reverse of that, that is x of 1 less than x of 2, but here, f of x of 1 is greater than f of x of 2, the graph is just going down. That's all that means. And then, x of 1 less than x of 2, but the function values are the same. F of x of 1 is equal to f of x of 2. Now, what I want you to see, there's two things going on with math. One, there's a graph, there's some image, right? But then what corresponds to that image is some kind of equation. Is that right? Is that right? Okay. So, if that's the case, then it's possible to consider the mathematics in terms of existing in two worlds. That is, there's what's called abstractions, and then there's what's called the exactness. The abstraction is actually said to be the equation, the formula, if you will. And then the exactness is said to be what I can actually see. Now, for mathematics, that was not typically the case. We call modern mathematics what you study now in terms of being able to connect the two. I have equations, and then I also have these graphs. But then if you connect the two, then we can talk about what's called analytic geometry. And I believe it was René Descartes, the French mathematician, who made that connection. Well, look at this graph here. And so the question is, use the graph to determine A, the open intervals of which the function is increasing, if any, and then B, open intervals on which the function is decreasing, if any, and then the interval if the function is constant. So, in terms of, for increasing it here, it has select the correct choice below, and if necessary, fill the answer box to complete your choice. The function is increasing on the intervals, what would you say? The function is increasing on what interval? Function is increasing on what interval? No one? Now let me say this. You come to my class, I expect you to be coherent to what I'm talking about. And if you're on your phone doing something else, then you can leave. If you're on your computer doing something else, maybe you did that for some other class or high school, I don't know. But for this class, for this hour and 15 minutes, we're on the same page. So I think that's very disrespectful of me if you're going to come here and you're doing something else. I mean, you can stay home. So the question again, what is the interval by which this graph is increasing? All right, let's see. The function is going upward, it looks like from 0 to positive infinity. Isn't it going up that way? So it's increasing, right? So we would say then on the interval from 0 to positive infinity is increasing. Now, so I'm just going to put on the side here, because I believe in my math lab, like once you click, then it opens up like another part of the question, and I don't have that, and I apologize for that. So let me just go ahead and just put on the side the decreasing part. So we have the increasing from 0 to positive infinity. So what would you say, what interval would the graph, that is the function, what would it be, where would it be decreasing? What interval? From what to what? Negative infinity to 0. Very good. And I'll just write this over here on the side. We'll put a bracket there because we'll say that it includes at that point. And 0 is always a funny number anyway in mathematics. All right. Use the graph here to determine the interval of which the function is increasing, A, and then part B, the interval which the function is decreasing, and then down below it breaks that down. So the interval by which the function is increasing, what would you say? Or here for part A, it has A and B, the function is never increasing. What would you say for this graph? So we said if it's going up, it's increasing. If it's going down, it's decreasing, right? So it's decreasing. So this function is never increasing. And so in terms of, I'm just going to highlight here for part B, in terms of this function decreasing, is decreasing on what interval? Negative 4 to 6. And we include the endpoints because they have, notice here they have the solid marks on the endpoint, right? Not an open circle. Okay. All right. Let's talk about minimums and maximums. Again, we call them relative, that is local, just maybe in a certain area. So we have this idea of a relative max that for some function at a particular value or point here at A, for this graph, we say that this function's graph has a maximum. And here's how we define it. It's because if there exists some open interval to some neighborhood about A, some interval on this x-axis, such that f of A, that's this guy right here, is greater than all the values of x on that particular interval. So we can say it's a relative. That is just local. Likewise, for a minimum or relative minimum, that it's just the lowest value. So here, f of b is less than f of x for all x that's not the same as b in some open interval, some local interval. That's what they're trying to say. That's what they're begging to say there. Again, you see he uses that word local instead of relative. Right? What is the difference between where a function has a relative maximum or minimum, and the relative maximum or what in the world? Is that saying the same thing? That looks funny. I copied that right out the book, but I don't think the wording is correct. What's the difference between a function that has a relative maximum or minimum and the relative maximum or minimum? Here's what I think he's trying to say, and the reason why I put that there is what I thought he was trying to say, and that is, what's the difference between a relative maximum and or just a maximum? Or what's the difference between a relative minimum and just a minimum? And if they use the word just minimum by itself or maximum by itself, and you don't see the word relative, then what they're actually saying is that that's an absolute minimum or an absolute maximum. Probably better to state that. Let's restate the question. What is the difference between a relative maximum and we call it absolute maximum? What is the difference between a relative minimum and an absolute minimum? Again, if it's relative, that means it's local. That's talking about just in some little neighborhood. Is there a minimum or maximum? We compare that to for the entire interval, not just for some local interval, but for the entire interval, is there a max or minimum? Let me give you an example, and then I'll move on. Consider y equal to x on the interval from, let's say, 2 to 6. So if we graph that, we start at 2, we go to 6, and something like this. It's a straight line. What is the relative minimum? What is the relative maximum? Okay, you're saying max and minimum. I'm dealing with the question of relative versus absolute. Yeah. Based on the definition of a relative, a relative minimum or relative maximum. It talks about finding some neighborhood on a open interval. Now this interval is going to be strictly closed, right? It's going strictly from 2 to 6. It includes the endpoint 2, it includes the endpoint 6. This line as it is has no relative maximum, nor relative minimum. It has an absolute minimum. That's the smallest point. It has an absolute maximum. It's the highest point. See the difference? Because it's a straight line, right? When you talk about a relative maximum, it's doing a Campbell's hump, right? It's curved. Just the maximum. The roller coaster, it goes down. That's the minimum. Right? We call those relative minimums, relative maximums. Now, I'll give another example. Let's state this. This equation based on the definition has no relative min or relative max. However, the equation has an absolute minimum at 2, 2, and an absolute max at 6, 6. Okay. That's the difference, ideally, between the so-called relative extrema. Again, the word extrema means maximum or minimum, and also the difference between that relative extrema with respect to an absolute extrema. Now look at this example, and then I'll move on. And I'll just give it here just in terms of a graph. Just claim some values. So this is 1, 2, 3, 4, 5. So -1, -1.5. So there's 2, 3, 4. So there's that point there, and I'm putting a closed dot. I mean, it's closed. This point here is going to be 5, 4. Right? So this point here is 4, -1.5. 4, -1.5. This value is 2, -1. This guy here is 3, 3. Let's call it 3. Okay. As my son Johnny says, we're just making it up as we go, right? I'm gonna show you. definition for relative maximum. See that hump right there at 3,3? That's a relative maximum. See this lower point here, 2, -1, and 4, -1.5? Those are relative minimums. See that? Yes, sir.
So both of those can be relative?
Yes, sir.
So they would both be included in that? Okay.
Because relative means local. Yep.
Gotcha.
Just within some neighborhood, do we get low value, decreasing and then increasing?
So anytime you would see those for those pairs, you would just include all of them because it's
Yes,
going to
sir.
be one of those at some point?
Exactly, yep. A function can have more than one relative minimum or more than one relative maximum. You see that value right here at the top, 5,4? What is that?
Your absolute maximum.
Thank you. Trying to get my karate kick. Just joking. It's an absolute maximum. Absolutely. Very good. So we say then that we have this guy is a relative min. This is a relative minimum. This point here is a relative maximum, and then this guy here is an absolute max. Just want to show you the difference between relative minimum, maximum versus, you know, some textbooks won't even use the word absolute, very elementary textbooks. But they're saying absolute minimum or absolute maximum. So we compare absolute minimax to the idea of relative minimum or maximum.
What about that first point?
I don't know, I just put that there. It's just,
Seems like non-existent.
I mean, no, it exists, it's a point, but in terms of the question of is it a minimum or maximum, think about it. There are higher points, right? So it's not a maximum. And it's not an absolute maximum, because that's the absolute maximum. That's the highest point. Now what I should have done was to kind of brought it down and did that like I did that over there. But I just made it up just right now. So you know, give me time to think about it and I'll give you a better graph, right? so he's just out there, right? But you have to love him. Put him on the team. Put him on the team. All right. In terms of symmetry, again, chapters 1 and 2 kind of looks like, as we go through this stuff, it's like bits and pieces of what they're trying to do is to give you bits and pieces of a graph. So eventually they're going to give you some function and they'll say, hey, just graph this function. And then when you're graphing that, you want to test, is there symmetry? Is it increasing here? Is it decreasing there? Is there a maximum? Is there a minimum? You know, that kind of thing. So in terms of the test for symmetry, it's just a mirror image. If you fold this first guy with respect to the y-axis, then obviously it's symmetric with respect to the y-axis. Now, when that happens, you're going to notice this is what you're going to have. You're going to have some form of x squared as the main term of the equation. And I'll show you that in just a minute. If it's symmetric with respect to the x-axis, then you're going to have y squared as the major term. And then this symmetry with respect to the origin is going to have some kind of form, typically some x to the third. So if it's symmetric with respect to the y-axis, if you negate the x value, or if you leave it positive, you still get the same y value. That happens with x squared, right? If I take 2 squared, I get 4. If I take negative 2, I still get 4. So now, look, sideways, look at this guy, it's the opposite that happens. Here, if I negate y, or if y is positive, I still get the same value for x. So here, if y is negative 1, I still get x equal 1. If y is positive 1, I still get x equal positive 1. Now, the symmetry with respect to the origin is pretty cool, because basically, the signs are supposed to run in pairs. If x and y are positive, then here, if x and y are positive over here, then for the graph to be symmetric with respect to the origin, then if I negate x, then I'm supposed to also get a negative y. So check this out. This guy could be in the first and third quadrant, but it can also be in the second and fourth quadrant. Same thing happens, right? So basically what I just said is what's here summarized in terms of this idea of symmetry with respect to the y-axis. And for me, here's what I do. Symmetry with respect to the y-axis, I'm thinking x squared. Symmetry with respect to the x-axis, I'm thinking y squared. And symmetry with respect to the origin, I'm looking for x to the third. Let's move on, right? All right. So just want to share that with you conclusively. If the equation contains an x squared only, then the equation is said to be symmetric with respect to the y-axis. Just what I just got through saying, but just want to make sure we state it there. If the equation contains a y squared alone only, then the equation is said to be symmetric with respect to the x-axis. And that's the example right there. X is equal to y squared minus 1. So you see that the y squared nature. If an equation contains an x cubed, x to the third only, then the equation is said to be symmetric with respect to the origin. Now it's pretty cool because if we reverse that, if we look at y equal to negative x to the third, then this graph does this. And so that is still symmetric with respect to the origin. So being symmetric with respect to the origin just simply means that the signs carry. If x is negative, then y is negative. If x is positive, here it's positive, positive, over here is negative, negative, and then this is negative, positive, and this becomes positive, negative. Just see that. If an equation contains both x squared and y squared alone, then the equation is said to be symmetric to everything. Right? You remember, if it's x squared, then it's symmetry with respect to the y-axis. If it was y squared, it's symmetry with respect to the x-axis. But if it contains both, ideally it may be a circle, and so if that's the case, then obviously a circle is symmetric to the x-axis, y-axis, and also the origin. All right. So without graphing, determine whether the equation has a graph that is symmetric with respect to the x-axis, y-axis, origin, or none of these. What say ye on this one?
Y-axis.
Okay, so you say the y-axis because you see that x squared, right? Very good. Check mark. Determine whether the, can you all see that? Okay. Now, if you look, if you can pull this same PDF up on your computer. So if you can't see it here, I apologize. But just if you have your computer, you can just pull it up on that so you can see it. Cause I know how it is when it comes to being able to see. 2 years ago, I had the LASIK and cataract surgery to improve my vision, and it's just all been downhill since that. So. Oh boy. So anyway, what about this guy? Symmetric with respect to the x-axis, y-axis, origin, or none of these?
X-axis.
X-axis, because it's that y square, right? Very good. So determine whether this graph of the equation is symmetric with respect to the x-axis, y-axis, the origin, more than one of these, or none of these. What do you say?
All three.
All three, right? Because it has the x square and a y square in there, so it's going to be symmetric to all the guys. Oops. Very good. Even and odd functions. The cool thing about even and odd functions is that you're still talking about symmetry with respect to the x-axis and the y-axis, just in a different way of saying it. I like to think about even function in terms of, like, if the leading term is x squared, or if that power is even, but the power is odd, we're typically talking about odd function. So here, if it's an even function, that is f of negative x, is the same thing as f of x. Well, that's what happens to x squared. We said that this guy was symmetric with respect to the y-axis. So symmetry with respect to the y-axis is synonymous to the function being an even function. They're saying the same thing. So for you, it's just trying to build up the vocabulary, so when you see something, you say, oh, I know what that is, right? So it's nothing major. If when we have f of negative x, that gives us a negation of the function, it is f of negative x equals to negative f of x, then we say that here the function is odd, or if you think about it, that's the same thing as what happens to x to the third. So here, odd functions is synonymous to here, the function graph being symmetric with respect to the origin. All right. Determine whether each graph of is the graph of an even function, an odd function, or a function that is neither even or odd. So we said that if it's an even function, you remember that's simply the same thing as being symmetric with respect to the y-axis, right? I'm sorry, odd function is the origin. All right. So what about part A?
Odd.
It's odd. Very good. Yeah, because that's doing this idea of symmetry with respect to the origin. So it's odd. Good. What about part B? Even, right? Because it's symmetry with respect to the y-axis. What about C?
Neither.
Neither. Yep. Is everybody okay with that? Okay. All right, determine whether each graph is the graph of an even function, odd function, a function that is neither even or odd. All right, so A, what do we have?
Even.
B,
Neither.
neither. C, very good. Yay. All right, so here, use possible symmetry to determine whether the graph is the graph of an even function, odd function, or a function that is neither even or odd. The function is, you look at this guy, so what do you say? This guy is even. And it's symmetric with respect to
Y.
the y-axis. Very good. Oh yeah, by the way, what I'm doing, and hopefully this is helpful, and this is one reason why I want you to pay attention, is we're just going over the homework problems, right? So that when you get there in my math lab, you'll be able to do them. Did I skip anything? Oh, that's the right one. Determine whether each of the following functions is even, odd, or neither, then determine whether the function's graph is symmetric with respect to the y-axis, the origin, or neither. Now, it's a couple of ways you can do this. The old-fashioned way is to run a negative through and see what happens with the output. If you run a negative through, if you get the original function, then we say that it's even. If everything is negated, then we say that it's symmetric with respect to the x-axis, excuse me. Or my way is I just look at it. Right? So here, this x to the third, which is the leading term, and then watch this x to the third. The signs are going to always be the same, right? If x is positive, then when I cube it, it's going to be positive. Same thing over here for x to the first power, because that's first power. 1 is odd, 3 is odd. So here, we say that this guy is symmetric with respect to the origin. Does that make sense? Yeah. And so that's the same thing as in terms of being what, even, odd, or so what is that? If it's symmetric to the origin, in terms of even and odd, we say it's odd. So the idea of an odd function is synonymous to being symmetric with respect to the origin. Saying the same thing. Really good. Here, look at the powers. The second power, fourth power, even. Right? Now look at this power for part C, x to the square, the second power, that's even, but this is x to the first power. So here, I'm going to get neither. See that? So either we're talking about a function that's completely even, it's completely odd, or it's neither. So let me write that down. So here, say that this guy is odd, even, neither. But let me show you how the textbook does it, and you just pick your way. I'm fine with either or. You can look at it and tell, and that's good. So the statement says that if f of x equals to f of negative x, then f is an even function. So for part A, we say f of negative x is equal to negative x to the third minus 6 times negative x. So I get f of negative x is equal to negative x to the third here, and this guy is plus 6. All right. I didn't finish. This statement here will actually go with part B. So note if f of x is equal to, I guess I should write it like f of negative x. If f of negative x is equal to negative f of x, then f is an odd function. Okay. That makes sense for part A. Because watch this. This guy is equal to negative times brackets x to the third minus 6x, which is equal to negative f of x. So if I put a negative here for x and run that through, I did that here. And if that gives me the negative of the function, negative times the original function to the function is odd. But if I run the negative through and I get the original function, then the function is even. Let's see what happens with part B. So g of negative x is equal to negative x to the fourth minus 2 times negative x to the second. This is g of negative x. If I raise negative 1 to the fourth power, that's negative 1 times negative 1, which is positive, and then negative 1 times negative 1, which is also positive. So I get positive x to the fourth minus 2 times, if I take this, here's what we're saying. Negative x is the same thing as negative 1 times x. So if I have negative x to the fourth, that's the same thing as saying negative 1 to the fourth times x to the fourth. Just get x to the fourth. Anytime I raise a negative, to an even power, it's going to be positive. So this is just x squared. But this guy ends up being the original function, g of x. So if I have g of x equals to g of negative x, well, let's look. If I have f of x equal to f of negative x, then the function is even. Right? That's what happened for part B. And then if I have f of negative x is equal to negative times the original function, then the function is said f is an odd function. And that's what happened for part A. Does that make sense? Does that make sense? So what I did was just to show you two ways of doing the same thing. Now you pick the way you like, and that's good. Okay. If you can look at it like I can, and look at those powers, you say odd, odd, odd function. Even, even, even function. Even, odd, crazy. Well, neither, right? So, good job. All right, the last thing for the section is the question of the difference quotient. Now, in terms of calculus, we've discussed already an important concept that you will definitely see again. And I mean, you get the calculus, and if you've had that before, you've dealt with the first derivative and then what's called the first derivative test. You want to be able to, the first derivative test simply says, can you determine the relative max or the relative minimum based on the derivative? But it's that derivative that's important to calculus and basically important to life itself. What would we do without a derivative, right? Well, who cares? you still live, but okay, this is a hard crowd. Man, I got to pay y'all more next time, okay? So this difference quotient, I raised a question a little bit later on, and I want y'all to investigate it. So I won't give the answer. I was about to tell you, but we'll get to the question in just a moment. But here, let's just do what it says. It says, find the difference quotient of f. That is, find. The question now is, what the heck is a difference quotient? It's a slope. That's all it is. That's all we're talking about. So this slope is said to be some rise over the run. This rise is the change, delta, the change of y with respect to the change of x. Well, the way it's written, it doesn't look like no dang on slope, right? Well, pictorially, if we can see that, it does. So, say for example, we have some point here that we call x, and then this is the function f, and then the corresponding value for y would be f of x. And then let's say that if I want to shift x over, because x, you're in my way, right? So get over x. I'm going to move x over h units. So this point here is called x plus h. And the function value is f of x plus h. Right. Now you remember the slope. We said that it's this rise over the run. That is the change of y with respect to the change of x. So we talked about y sub 2 minus y sub 1 over x sub 2 minus x sub 1. All right, so theoretically, this is x sub 1. This whole guy right here is x sub 2. This is y sub 1, just to match it up with the formula. And this is y sub 2. So to put that into this formula here, what we have is the y sub 2, which is f of x plus h minus y sub 1, which is f of x. And that's all over x sub 2, which is x plus h, minus x sub 1, that's minus x. Now you simplify that. I'm going to simplify it over here. We'll put it right here. So we get the slope. Notice that in the denominators is x plus h minus x, so the x's cancel. So you just have left f of x plus h minus f of x all over h. Now do you believe me that the difference quotient is a slope? Okay. And in calculus, it becomes a most important slope. Don't forget it. You'll see it again. What we do in calculus is we just put the limit notation, the limit of this difference quotient as x gets closer to h, what happens. See this difference quotient right now, if it's a slope, if I connect these two dots, I get this straight line. That straight line is actually a secant line. Right? So the difference quotient is the slope of the secant line. But if we tend this h, make h small, keep making it small. When I make it small, when we make h small, these values on this graph tend to get closer and closer back to this x value. And what happens is you look at the slope as it changes. that becomes a limit, and that becomes something important to mathematics. And that becomes the wave of all of engineering, science, and physics. Tends to be, and economics itself is based on that model. So, I digress and just work the problem for you. Okay. So, this f of x plus h, basically that says when I see x, I'm going to replace x with x plus h. So this is negative 9 times parentheses x plus h minus f of x. I'm going to put that in brackets. F of x is negative 9x plus 6 all over h. And just simplify. Again, this part is all of that, right? And this part is that. So we simplify, we just distribute, so we get negative 9x minus 9h plus 9x plus 6 all over h. Let's see if anything cancels. Well, the negative 9x plus 9x cancels. And we have left I'm so sorry. I forgot my 6 over here. Dang gun it. I'm so sorry. I hadn't been wrong since 1978. I apologize. No, I'm just teasing. I was only a lad in 1978, but times were so much different then. Anyway, what'd you say? That's funny. So that's just the first part there. I replaced the x with x plus h, but that function is still carried over to that plus 6. I'm so sorry. Then this is minus f of x, negative 9x plus 6 all over h. Now we simplify. So this is negative 9x minus 9h plus 6 plus 9x minus 6 all over h. Negative 9x plus 9x cancels, 6 minus 6 cancels. So I have left negative 9h divided by h, then the h's cancel. I have left just negative 9. Now a little bit later, and you've probably seen it before in previous math classes, this is the slope-intercept form, right? Y equal to mx plus b. You remember that? Right? And so if it's written in that form, that's the equation of a line, and that number multiplied to x is the slope. Right? Well, I just told you that this difference quotient is what? A slope. So I get the slope, which is negative 9. Now that works out very easily for linear straight line equations. But in life, we have more than linear equations. We have equations that are quadratic and hyperbolic and ellipsoids and paraboloids and all those other loids, right? So, and so the neat thing is, you know, if it's a straight line, you can find the slope. But is there a function such that I can find the slope for any, let's say an operator, that I can find the slope for any function? Yes, it's called the derivative. All right. Let's do this last one here. Where's my question? I thought I had a question. Oh, there it is. I'm sorry. In mathematics, the difference quotient has another meaning if interpreted with respect to slopes, and h is allowed to change repeatedly if the difference quotient takes on new meaning. Describe and explain this phenomenon. That's a good question for you. All right, look that up, it may come up again. One more, and let me just pick the last one to do, because this is more into it. Probably won't finish it, so, because of the time, but we can take a stab at it. So here, this becomes 2 times parentheses, wherever I see x, I'm gonna put x plus h to be squared, plus x, but this becomes x plus h, minus 1, and then now minus the function f of x, minus the brackets 2x squared plus x minus 1. That's all over h. So we simplify this. So this is 2. We FOIL that out in the parentheses. That's x squared plus 2xh plus h squared. This is plus x plus h minus 1 minus 2x squared minus x plus 1. I forgot to close that parentheses up right there. That's all over h. All right, distribute that 2 through that the first terms there, so that's 2x squared plus 4xh plus 2h squared. I can cancel while I'm there. This is x minus x, 1 minus 1. Don't need to bring that stuff over in the new year, right? Plus h minus 2x squared all over h. Now something else cancels. You see that? You see the 2x squares cancel? And so I have left here, this is 4xh plus 2h squared plus h all over h. Notice I have an h common in my numerator. Let's factor that out. So this is h times parentheses 4x plus 2h plus 1 all over h. Now I cancel out the h, and I have left what I want for the so-called difference quotient, and that is 4x plus 2h plus 1. Right? Has anybody had calculus before? Okay, so I was going to ask you what would the derivative be for that, but you'll get that in a couple of semesters. Hey, you all have a good weekend, and you all take care. Thank you.